So this kind of problem, we've been seeing a few like this recently. So I hope I can see only 3 of you got this one right. But hopefully it's something that you can look at and make sense of. So really the only question, they give us a lot of information, but the only thing that really matters right here is that they're trying to ask, how do we increase the power of the test? What's going to give us the greatest power? We already know that what the effect size is, so we can't change that. And the effect size would just be where the true population is versus what the the sample population or the sample is. I cannot talk. All right, so anyways, we have the effect size. So the only thing we control is the significance level and the sample size. And if the significance level is higher, that means our power goes up, because this gives us more ability to reject the null, a higher significance level. So we're going to be going with either A or B. We want a higher significance level. And also the higher the, if I can think, higher the sample size, the narrower our distributions will be. Instead of being more spread out, they'll be a little more narrow in their distributions, and there's going to be less overlap as a result. Maybe not the way I drew it, but the way it would work out in reality. So anyways, the answer here is D. We want a higher significance level and a higher sample size. So that will increase our power. We can't say right now exactly what it will do, but it will be the highest power, that's for sure. Okay. Okay, let's see where our progress has taken us so far. Looks like we've made it all the way down to Indian Canyon. And that's as far as we're getting there at separation. And then it's just review for the last little float. Just remember that. And there's not a whole lot going on right here. We've got just a image from the river. People in 5th hour were concerned about that poor kid drowning in the river. But here's, we got our view. It's not a bad view at all. We'll just do a quick panorama look around and then get back to some statistics. All right, so there is Indian Canyon. It's just a nice, relatively smooth, flat area of the river, which hopefully that's how you're feeling right now. You're like, it's smooth, I got this. Statistics is going well for me. I just aced that last test. I hope everyone's saying that right now. And now you're going to get ready to ace your next test, which will be dealing with chapter 26. Hopefully you read that, so you're already prepared for today, but we're going to run through one part of it. And well, let's just get going. So imagine that there is a list of 900 data points. It actually doesn't matter what the data is referring to, but let's just say this data set, which has 900 data points, could take on any numerical value. And just to remind you what numerical values are, there's a few right there. 1, 247, 8 million, whatever. How many of these points would you expect to have a leading number of 1?
One-ninth.
1/9 of them. Yeah, so 900 data points, 1/9, 100. Yeah, you might expect 100 of these to start off with a 1. So if we keep going, how many start with 2? How many start with 3? What would you say for, no matter which number I give you, how many should start off with that number?
One-ninth.
1/9, yeah. So sorry to start off with such taxing questions. I know it's a rough way to start off class. So, I mean, intuitively, we would think that any random list of numbers, as long as it's, kind of enough of them right there, that you should have approximately equal amounts starting with each digit. Well, in the 1930s, and this is actually discovered or observed before that, but in the 1930s is where it kind of got formalized. Frank Benford looked at a number of data sets, and he looked at a lot of data sets, ended up with, I think, over 20,000 data points that he looked at and examined from a lot of different data sets, and found that the leading number for each data point was not distributed proportionally. So even though you might expect each leading number to be, occur 1/9 of the time, or about 11.1%, that's not what actually happens. So the distribution, which is part of what we call Benford's law, follows a very specific distribution, and it looks like this. So numbers starting with 1 happen about 30.1% of the time. I'm not going to read all the percents, but you can see it gets less and less percent all the way down to 9. And this is a mathematically derived law, and it does show up over and over and over again for a lot of data sets. So we'll get into the reasons behind it just a little bit, because that's not the purpose of our lesson today. But it does have to do with logarithms, and it has to do with logarithmic growth. All right, so if you've ever seen a logarithmic chart, it looks something like this, a logarithmic number line. They're not distributed evenly. So if here's, let's start off with 10. This is 100, and this is 1,000. I can't quite fit the 1,000 in there because I went right up to the edge. But a logarithmic chart looks something like this. It gets smaller, and then so they get closer and closer as you get up. So it doesn't distribute evenly. So it kind of follows the same distribution. All right. Maybe I'll talk a little bit more about the reasons behind it, but that's enough for right now. So there you go. So I guess that's what we're getting into right here. This is true of many data sets, but for this to be applicable, it must include values of many different orders of magnitude. So if you have hundreds, thousands, and 10,000s and so on, just a lot of different data sets, that works. And we're about to test a data set to see if the distribution holds. But there was an example given. It's funny, I was actually listening to a podcast about this. If you're familiar with Radiolab, they've done some stuff on this. And anyways, I was listening to this yesterday. It'd been something for me to listen to. I was just sitting down for a long time. Then I listened to it. I was like, oh, this will be perfect for class tomorrow. So that's kind of where this comes from. And an example came up of what about if you looked at, they used the example of New York City. If you took everyone there and looked at their bank account, how much money is in their bank account right now, that would follow Benford's law almost perfectly. Because you're going to have people with maybe even just like less than $100 in their bank account, and people with thousands of dollars, people with tens of thousands, or even hundreds of thousands, I guess even beyond that too. But all kinds of different orders of magnitude as far as how much money is in the bank, and it will follow this breakdown. Okay, so it has to include lots of orders of magnitude. And yeah, I'm not sure anything else that I need to say about it. If you find it interesting, I just look up Benford's law and you can learn more about it. So here's what we're going to do. Here's our interest in this today. We're going to test a different data set to see if the distribution breakdown holds. And we're going to be looking at the 58 tallest buildings in the world. Now, I don't have a list of this. Now, maybe I should have done that. I kind of simplified this for us a little bit so that we could just jump right into the calculations. But the 58 tallest buildings in the world, if you just look at the leading digits of that, I've got that summarized for you right here. So the leading number for all the tallest buildings in the world, this is in meters. 24 of them start with a 1, and then so on from there. So just initially looking at this, does it seem to fit the distribution? Or does it seem to fit Benford's law, I should say?
How many buildings are there total?
58. And don't worry about calculating percentages. I'm going to show you that on the next page. So just an initial glance, that's all I'm asking.
I don't know, because like for the leading number of 5, there's only 1, which is 7.9%. But then for 6, there are 5, which is 6.7%. So that's like doesn't really make mathematical sense.
Sure. I'm glad you're noticing that. Yeah. So obviously we're not going to match it perfectly. So actually, let me just jump to the next page, because here's where I include the percents. So now you can kind of do some comparison and see, and you have to kind of decide for yourself, does this seem to fit or not?
So yeah, kind of.
Okay. And you might have your own opinion on it currently. And of course, what we're going to be doing is we're going to be testing to see if this distribution does match, or it's going to be a significance test. So essentially we're saying, do we have evidence that this does not match the predicted breakdown? Okay, so that's just to set you up from the beginning. That is what our chi-square test that we're going to be looking at today is going to allow us to answer. So we can look at this and we can have our own intuition of whether this fits Benford's law or doesn't. But we're going to test it to see if we have evidence to reject the idea. So we'll assume that it does to start off with. Okay, and we'll get to the hypotheses later. So the important thing is, well, not the most important thing, but kind of the starting point, I should say, is that we are looking at a chi-square statistic. And this, so I'll just read this. So it kind of seems like it complies with Benford's law. Maybe it doesn't. So we're going to check this more accurately to see if this holds true under statistical scrutiny. All right, so we're going to calculate a chi-square statistic. And this is it. This is actually straight from the AP formula sheet. It's the sum of the observed count minus the expected count, and then square of that divided by the expected. Now this will hopefully look somewhat familiar because this is very close to our standard deviation our standard deviation formula, which I mean, if I need to rewrite that one, it's something like the sum of x sub I minus x bar squared over n minus 1 square root of that whole thing. I might have actually messed up the formula a little bit, but you can see it does look somewhat familiar. Okay, so they're not related especially, and I'm going to kind of go through and explain why we have it set up this way. But at the very least, if you remember, we only calculated the standard deviation we only calculated it once because it's very time consuming. You have to do a different calculation for every data point. So if I have 100 data points, there's no way I want to go through and calculate a standard deviation for that. That's why we let the calculator do it. We're going to calculate a chi-square statistic by hand. And we'll learn that this isn't something that we want to do by hand very often. All right. So the only change that I did here was I changed this into counts. So what we have are 9 categories. And I want to emphasize this now and re-emphasize it later. We're dealing with categorical data. And it might not seem like it, but remember, the category is, what is your leading digit? Oh, if it's a 1, you fall into this category, all the way up through 9. So we have the counts. There were 24 of the 58 buildings that fell into this category. Now, what I did for the expected was I took Benford's proportional breakdown, which is 0.301, and just multiplied it by 58 buildings, and I got our expected count. So out of 58 buildings, if it complies perfectly with Benford's law, then we should get 17.5. Obviously, we're not going to get decimals, but it's important for our calculation. Okay, so hopefully everyone's good with this logic so far. And what we want to do is we want to calculate for every single category, and we've only got 9 to work with. We want to calculate, first of all, let's do the observed value minus the expected value. So I'll only do the first one, 24 minus 17.5 equals 6.5. And now I just want people to randomly pick one of these, and whoever kind of picks which row they want to do, you can kind of do the calculations the entire way through, but just do observed minus expected for now. Okay, so we got the observed minus the expected. This is telling us how far off from what we expected to get. I mean, that's straightforward, right? So now what we want to do is we want to square that value. Just like we did with our standard deviation, the idea is we want all these to be positive values, first of all, and then the squaring has some mathematical reasons later on, not for us, but at least with standard deviation, there's a reason for squaring it rather than doing something else. And so we want to square this basically for our purposes just to get positive numbers. So I'll take my 6.5, square it, and I got 42.25. And you guys can fill in the table with yours. Okay, so we did observed minus expected, squared it, we got our numbers looking good so far. Now keep in mind that these numbers could get really, really wild and out of hand. Imagine if I had changed this by an order of magnitude. There were 580 buildings and 240 of them were observed with a leading digit of 1, and then 175 of them were expected. Well, then this gets out of control and I'm up to 4,225 rather than 42.25. So these numbers that we're working with aren't especially big, but you can imagine it can get out of control. Now we need to have kind of a standard for all this. And so what we do to establish that is we divide by the expected value, because the expected value will grow with the sample size. Okay, so if we did have 180 buildings and now we had 175 that were expected, then that would kind of grow and help to limit the kind of crazy numbers that can exponentially grow from this, if you're following the logic there. So this helps us get back down to manageable numbers and kind of standardizes our chi-square statistic that we're going to derive right now. So I'm just going to take, what I want to do is take the 42.25 that I got, divide it by the expected value right here. So it's going to be 42.25 divided by 17.5, and I got 2.414. And none of these calculations are hard, but go ahead and fill out the rest of the table. All right, so we did this as a group effort, which made it go very quickly. But you can imagine if you had to sit here and do all these calculations by hand, it would not be very fun. You could set this up in a spreadsheet. Hopefully you guys are learning Excel and stuff like that. But you could do this in a spreadsheet, make it take not quite as long. But anyways, doing this by hand is no fun. And just as an early spoilers, we are going to learn how to do this on the calculator. But by working as a group, we can get it done pretty quickly. The last thing we need to do, now these are the individual contributions toward our chi-square statistic. And remember, I'm going to go back one page real quick. The formula is that it's the sum of all these calculations, sigma, all that stuff we just did. So we want to go through, and these are considered the contributions to the chi-square. And now we can add it all up. So everyone can add those numbers up and we'll see if we did it correctly. Okay, so we added this up when we came up with our chi-square statistic. And this number right now has just about as much meaning as when we calculated a t statistic or a z statistic before. So if you got a t of negative 2.193, that on its own doesn't answer the question of whether something is statistically significant. Now we have kind of an interpretation of this, or we're like, okay, that's just over 2 standard errors away from the null hypothesis mean, and we can kind of understand that. We're going to talk a little bit more about the interpretation as 8.821, though it's not going to be as neat of an explanation. All right, so let's kind of just work with this for now. We have this 8.82, and I'm going to, in fact, on the next page, we'll have that number. So There it is, 8.82. We did do it correctly. That's approximately what our chi-square statistic is. So what does that mean? And we're going to have 3 different chi-square tests. And today we're going to be using our chi-square for the chi-square goodness of fit test. And before we can answer exactly what this 8.82 is, we're going to go through a few more things, and then we'll kind of put together what that means. This is the definition from the textbook. So it's actually a pretty good one. The chi-square goodness of fit test is a test of whether the distribution of counts in one categorical variable matches the distribution predicted by a model, and the expected counts will come from a predicting model. In our case, it was Binford's law. And the test finds a p-value from a chi-square model with n-1 degrees of freedom, where n is the number of categories in the categorical variable. We're going to come back to this one. In fact, that's going to be on the next page. But you will see goodness of fit sometimes abbreviated to GOF, which is how it will appear on your calculator. And we'll get to that before too long. So again, before we jump into calculations, notice from the definition that we are dealing with categorical variables. When we were dealing with our z-tests, just a second, our z-tests and t-tests and t-intervals, everything else, those are quantitative variables. And the one thing you might be saying is something like, well, with proportions, those are categorical in a sense. Because if you have a proportion of people who like vanilla ice cream is their favorite, right? So proportion, that's a category, right? You could have 100 people give their preference and 54 of them prefer vanilla. You know, so it's categorical and we turn it into, you know, a proportion. So we are dealing with categorical variables when it comes to proportions, but the difference is we're only dealing with two categories. Either you fall into this group or you don't. And the difference with chi-square is we just had 9 different categories. And we're going to check to see if all of them fit what's expected and how much it varies from what we would expect. So it's one thing to say, oh, okay, so this 0.54, is very close to the null what we would expect from the null hypothesis. So therefore we don't reject the null. We're only testing one thing. We wouldn't want to go through and have to do 9z proportion or one sample proportion. I can't think, but you can get it across. We don't want to have to do 9 tests to get that done. So the chi-square can kind of tell us, does this distribution overall fit the expected distribution? Do the counts match? So we're dealing with categorical variables with multiple categories, at least, well, and we'll figure that out. We're dealing with counts. And that's why at the beginning I changed everything from the percent breakdown to predicted counts, just because generally that's what we want to be working with. All right, let's see. Because this can only be calculated by performing calculations on every data point, we are not going to be doing this calculation by hand usually. Imagine there were hundreds of data points. That would just take so long, and your calculator can do it much easier. And just to contrast that against our inference tests, even with the most complicated test that we did, and maybe you think the 2-sample t-test was the most complicated. Well, that required, let's see, you needed x bar sub 1, you needed s sub 1 and n sub 1, you needed x bar sub 2, s sub 2, and n sub 2, and then you needed your degrees of freedom. You needed 7 numbers to do that calculation. Even the most complicated that it got, you needed 7 numbers. But with a chi-square, you could need to do thousands of calculations, and that's just not feasible. Okay. So if we go back to this, we want to determine if the data match the predicted distribution or not. And we're going to start with our hypotheses. I already kind of talked about this, so maybe we can go over it quickly. So the null hypothesis is that our claimed distribution is true, and therefore, in our example, we said Binford's law is true. Okay, so it's going to match the distribution predicted by Benford's law. The alternative claim is that the claimed distribution is not true. So that, and maybe I need to rephrase this. It's not that Benford's law is true or it isn't true. It's that Benford's law is applicable or Benford's law is not applicable. So those are our two hypotheses. So our null hypothesis is the no change, in which case that means that it does follow Benford's law like we predicted. It's worth pointing out right here that sometimes the assumed distribution is just a flat one. So you might come across a problem that says someone is suspicious that a die is weighted. So it rolls, 4 or 6 or something more often than it should. And then so of course we'd expect it to get 1/6 of the time every single time you toss it. There's an equal probability, so we should get a pretty even distribution of 1s, 2s, 3s, 4s, and so on. So you can have an even distribution, and oftentimes that's actually what you're going to be testing, that it's an even distribution. Now, we want to convert this into counts, so we would roll a specific number of times. So maybe our 1s, we rolled, let's say we rolled 48 times, just so we have a multiple of 6. We rolled 48 times and I got 10 1s. Now I would predict 48 divided by 6, I'd predict 8. All right, so all of these would be 8. So that would be the counts that you're testing against. All right, does that make sense? And again, it's a rhetorical question here. Think about it, and if it doesn't make sense, you can flag that idea. So you have to kind of base that on your different problems. And I will kind of give you a little bit of an example of that at the end of class before we leave. So another example of this would be the expected number of each color in a bag of M&Ms. I would initially assume that all colors are equally represented. So I might test that theory. Okay. So we need to know degrees of freedom before we can finally jump into the final bit of this. In a goodness of fit test, the degrees of freedom will be the number of categories minus 1. So in our example, there were 9 categories. We had 9 leading numbers, so our degrees of freedom is just going to be 8. It's very important to emphasize this right now, that you figure out how many categories are in your data set and then do minus 1 from there. And there it is, just big and bold. So if you look back on this presentation, you can have it. Okay, so this is what we're working with. We have our degrees of freedom, our chi-square, we have our 2 hypotheses, and our alpha level we'll set at 0.05. We can set a significance level, whatever we'd like. All right, with this information, now we're going to use the very last table on our formula sheet. We are almost done with going over everything on that formula sheet. That should make you feel pretty good. So we're going to look at table C, which is your chi-square critical values. I'm going to bring that up on the next page in a second. But what we want to do is we want to look at the row for 8 degrees of freedom and see where our chi-square value of 8.82 would land. And this is what it looks like. The only thing you're missing from this is the actual chi-square distribution, which I'll talk about that later. So of course, I've got row 8 right here, 8 degrees of freedom. I want to move across, and I'm going to look at this in 2 different ways. I'm going to start off with this 8.82, but I'm going to realize that I don't have 8.82 on this row. As I move from left to right, it gets bigger and bigger and bigger, and you see it maxes out at 27.87. So we don't have 8.82 anywhere on this chart. So I'm going to pretend, now I'm going to come back to 8.82, but I'm going to pretend that we got, I'm just going to pick a random number, 15.38. I'm going to pretend that we got a 15.38 instead. So what I'd do is I'd move across until I found where 15.38 landed, and it looks like it would be right there. Okay, make sure I'm on the right row, and I am. So anyways, it looks like 15.38 would be, if this is a number line spectrum or something right there, it would land pretty close to that value. So what this tells me is that my p-value is found right here. You can see the p. So this is telling you what the tail probability is. So 15.38 would fall somewhere between 0.10 and 0.05. So my p-value, all right, is going to be, oops, got to do this the other way, less than 0.10, but greater than 0.05. Now, if you remember, we kind of looked at how to do this with our Z and T tables also. So we can get accurate enough with this, because the only thing that really matters for us is this p-value bigger than or less than our significance level? And assuming that we had this as our chi-square, this is going to be just bigger than our p-value. It would be, I'm just going to pretend it's like 0.06, and which is greater than 0.05. I don't know that it's actually 0.06, but that doesn't matter. It's bigger than 0.05. All right, so hopefully that logic is making sense. Now in our specific case, our chi-square was 8.82, which is actually off the chart on the left side. So if I look over here, the only thing I can tell from this chart is that it's going to be, and if I notice that my tail probabilities keep getting bigger and bigger as I go right to left. So I know that my p-value is going to be greater than 0.25. I don't know the exact value, but the biggest p-value that exists is 0.25. And I know that 8.82 is going to be off the chart to the left, so my p-value is bigger than 0.25. Again, this is sufficient for what we need. But there's, of course, an easier way of doing it, which we'll see on the calculator. All right. But hopefully everyone's good with that. It's important to know the tables just so that if there's an interpretation question where it requires you to use a table, that you're not lost on that. So of course, start with your degrees of freedom, figure out where your chi-square falls on it, and that'll tell you what value your p-value is going to be between. Okay, I think that's enough said about that. So that's where we are. It turns out our value is off the table to the left. There's a greater than 25% probability of getting results like the ones we got by chance alone, assuming the null hypothesis is true. Therefore, we don't have convincing evidence to reject the null hypothesis. Our p-value, we're just going to use 0.25 right here, is greater than 0.05. We fail to reject the null. And at least according to this data set, it seems like building heights follow Binford's law. All right. So just to clarify that a little bit, get to this one right here. This distribution, which does not match Binford's law very closely, well, I mean, you can see we're 10% off right here, and we're 6% off right here, but this is still close enough over the over 9 categories that we could still basically assume that Binford's law holds. We cannot reject that Binford's law is what's really going on here. Okay. And let's see, we got past that. So now we can do this in a more efficient way. We can save time. We can get a better answer rather than just saying our p-value is greater than 0.25. We can figure out exactly what it is using our calculator. We're going to put our observed values. I'm going to run through the process, and then I'm going to go back to the data set so you can plug it in. So we're going to put the observed values, and I shouldn't say observed values, sorry. I'm going to put the observed counts in list 1 and the expected counts in another list. And then you can navigate, and I encourage you to do this right now. Go ahead and navigate HipStat over to tests, and then you can go, it's close to the bottom. Option D is your chi-square GOF test, goodness of fit. And if you even go into the test right now, you can see all it's asking for is the appropriate list for the observed and expected, and then your degrees of freedom. Okay, so we could only get accurate enough to say it was greater than 25%. Let's figure out the true one. I'm going to go back now to this page. No, it's not this one. I'm sorry. This one. Let me clear my writing. All right, and now you can plug your observed in on list 1, your expected in list 2, and then just go back to your stat tests, goodness of fit test, use those 2 lists and figure out your chi-square statistic and your p-value. Okay, and for those of you who did get that fully calculated, someone can write down what is the true p-value for this particular problem. Okay. Yeah, so it rounds to basically 0.36. I think you guys should have seen 0.3575. All right, so yeah, that's it. And again, does that really help us more knowing it's 0.35 rather than greater than 0.25? Not really, but I mean, it's not too difficult to have your calculator do that. So here's where we can take advantage of the technology. And in fact, one thing I want you guys to do is to go back into your chi-square test and keep everything the same, but at the bottom where it says calculate, you can go over to draw and you can just pull that up on your calculator. And I'm going to show what that looks like right here. So you see this skewed right distribution, and all chi-square tests are, all chi-square distributions are skewed right, though the higher your degrees of freedom, the more normal they look. So if you wanted to pretend like you had all these numbers, but with higher degrees of freedom, you could just keep changing your degrees of freedom, see how that changes it. And you see that you end up with this kind of shaded in. And at the bottom of the screen, it still tells you your chi-square and your p-value. The one thing that your calculation will do is it'll show you the contributions. That if you notice that very last row, it said contrib, and that means basically it's abbreviation of contributions. And if you scroll over on that, you can see all the different last column values that we had. So I had like 2.414, and then it was 0.141, and all those different values that we added up show up in that, so that you can kind of see what's going on. But just to talk about this distribution a little bit, with chi-square, the only thing we can ever test is that all of our categories follow the distribution that we expect, or that our distribution does not follow it. So we can't test that it's greater or less than. So we don't have a 1 or a 2 tail. And you'll notice that you always end up with just a right tail for your chi-square. Your chi-square value gets bigger and bigger. And depending on your degrees of freedom, your significance level, all that stuff, that'll change where your significance cutoff is. So it really kind of functions a lot the same way that you've learned to expect, but you know, your cutoff at a certain point, in order for this to be statistically significant and fall above, let's say this was a 0.05 level right here, you're going to need a pretty big chi-square value. And again, that kind of helps to explain why those numbers get higher and higher on the table. Because I'll go back to the table real quick. And notice that if you want to have something significant at the 0.0005 level, that's a high level of significance, then you need a huge chi-square value compared to just the 0.05 level. Well, I mean, that might not seem huge, but it is a difference there. So to actually get the cutoff, you're going to need to get a bigger and bigger chi-square. And then the way to interpret this really hasn't changed either, in that the area underneath this curve is still 1. So we're still looking at a 0.05 area underneath the curve. And we're basically saying there's some kind of a critical value right here that we saw. It was like 44 point something if we wanted a 0.005 significance level. So this 44 point something would be our critical value, and we'd need to get that value or higher in order to get a p-value of 0.0005 or lower. Okay, hopefully that's helpful to understand the chi-square distribution and it doesn't confuse you. So this is your homework. Of course, it's on Canvas, but before we left today, the last thing I wanted to do is just look through one. It's one of your actual homework problems. In fact, it's the one that you have to turn in. I wanted to just get it started so you could understand something about it. So I'm going to stop sharing and pull up your textbook and then share that with you. Okay. So this is problem number 9, and I wanted to kind of run through this so you knew how to get started. And so if we look at this, offspring of certain fruit flies may have yellow or ebony bodies and normal wings or short wings. Genetic theory predicts that these traits will appear in the ratio of 9 to 3 to 3 to 1. And that's explained. So 9 out of 16 should be yellow and normal, 3 should be yellow and short, 3 should be ebony and normal, 1 should be ebony and short. And a researcher checks 100 such flies and we get a specific distribution. So now the question is, does this match the theoretical distribution? So before we can just run through that, I want to, first of all, think about how many categories do I have for this?
Four.
I got yellow normal. Oops, I don't have my pen on. I got yellow normal, yellow short, ebony normal, ebony short. Okay, so the actual, I'm going to put observed up here, and I'll put expected in a we'll figure that out. So the observed values are given. So I've got 59, 20, make sure I got that in the right order. I do. 11 and 10. The expected values. Now we can't just, we have to plug this in. We have to get it right. So 9, the ratio is 9 to 3 to 3 to 1. So that means out of 16 possible outcomes, 9 of them should be yellow and normal. So that means if there were 100 flies that we were checking this against, the distribution should be 9 out of 16 times 100. So if I multiply that out, you guys can do the same. I get 56.25. Okay, so I need to calculate to figure out what my expected counts would be. And I won't do the rest of it, but the, you can fill in what these 3 values are, and then it's straightforward, put it into lists, let the calculator run the test for you. Now, what's our degrees of freedom for this problem?
$99.
Not 99. It's a good guess. Because if this was a like a one sample t-test, we'd look at the sample size and subtract 1. But we had to do it a little differently for this chi-square test. Anyone else brave enough to guess?
Would it be 3?
It's 3. So remember, it's your number of categories minus 1. And we have 4 categories. Those are right here. So that is what you need to be thinking about. This is a little bit of a change. Doesn't make the math difficult at all. But 3 degrees of freedom for this problem. So regardless of whether you're using the table or your calculator, you want to plug in 3 for that and move forward. All right, so that's all I was gonna do. You can find the homework still online. So if there are any questions, okay, I see, Jose, you put 3 in the chat as well. So if there are any questions, you can stick around, but otherwise just kind of work through that homework tonight to get comfortable with chi-square. Of course, we'll talk more about that the next 3 days. So have a good day.